Okay, so I'm gonna go over 3.3 quickly. It's the heating and cooling of building. Okay. So Newton's law of cooling. Let me introduce Newton's law of cooling. It says that the rate of change in the temperature T. So here T is the temperature inside the building or the temperature of the medium. Okay. So give me a second. Yeah, this is equal to some constant. The property of constant depends on the property of physical property of that building times the difference between the outside temperature and then inside temperature. Okay. Okay. So give me a second. So I introduced T, right? And then N. There is other one, H of T. That's the rate of increase in the temperature caused by people and then some machine. This is a rate of increase in temperature by people or light bulb, right? Light and a machine. Some air condition or something, computers or some, some kind of heat source or cooling source. Machines inside the building. And the U of T is equal to a rate of increase or decrease. This is in temperature. Let me say just T and P stand for temperature and caused by air conditioner. Oh, sorry, the air conditioner, especially in the U of T, not H of T. Sorry, is air conditioner. Let's see example. So oh, sorry, before doing that, if we just adding H and U in the Newton's law of cooling, then the differential equation becomes like that. So K times M, right, minus T, and then plus H plus U. Okay. So so here H is all H, because H is always greater than or equal to 0 for any H. Okay, this means for arbitrary T. Okay. And then this is the air conditioner or furnace. Furnace is, I think, a boiler in Korean. Okay, so the U of T, so U of T is positive if for what furnace, right? Negative for AC, air conditioner. Let me say just AC. Okay. Let's find out the general solution. Okay, so this is the linear differential equation, right? Okay, so I mean, assuming that M, D, H, R, U are linear, then it's going to be linear differential equations. So see example 2 in textbook. See example 2. So just please read it, the problem by yourself. The example says that T of 0 is 35 Fahrenheit, okay, and then T of 3 is 40 degree Fahrenheit. Okay, so I think they want to find out the temperature of the beer Okay, and then initially 35 Fahrenheit, and then I think the the beer is on the table in some restaurant, and then in a summer maybe. So the temperature of the restaurant is the quite you know the uh, the maybe just a little warm. Okay, I think there is air conditioner, but we just ignore that. Furnace or air condition. So in the view of beer, outside temperature here, outside temperature is what? Outside temperature means that the temperature of the restaurant. Okay, there is 70 degree Fahrenheit. Thus, what? M of T is 70, 70 to 70. Okay, so the outside temperature M of T is a constant function. Okay, and then we ignore the heat source and it's a furnace and air conditioner. Also, we ignore that, so 0. Okay, so modeling differential equation, then using the Newton's law of cooling, then dt over dt is plus k times t is equal to k times m, by the way. And here m is 70, right? Okay. So now then dt over dt is equal plus kt is equal to 70k, right? So this is linear, by the way. This is linear. Let's find a general solution using the method of integrating factor. Okay. So using the method for integrating factor. Okay. So now the mu, we will find the mu, right? Integrating factor mu of t is equal to e to the integral, what? P of t dt, right? So I think we need to figure out p and q right there. So here, what is it? P of t is k, right? And then q of t is 70k, right? Okay. So now this is equal to e to d integral k dt, which is e to d kt, right? Then t of t implies t of t is going to be e to d minus kt, right? T times integral e to d kt times 70k in the dt, and a plus c. So this is equal to e to the negative kt times integral of this is what? 70k times square e to d. Oh no, just 70, right? Oops, 70 times e to d kt and a plus c, which is 70 times 70 plus e to d, not e to d, yeah, c times e to the negative kt. Okay. Okay. So as you can see that, if t approach infinity, this term explains the term just gone. So the temperature of the beer approaches 70 eventually as time goes on. Oops, sorry. Okay, but let's find out. This is general solution, by the way. That's a general solution. Let's find a particular solution because the initial condition given, right? You see that? T of 0 is 35. Let's find out then K2. Okay, we didn't figure out K. Yeah, so let's find out C constant integration and K. Yeah, let's find out both. So T of 3 gonna be what, 70? Then I just substitute 0 and 3 into the general solution. Okay. So we got T of 3 is 70 minus 35, and the e to the negative 35k, right? So that must be equal to what? The problem says that is equal to 40 degree Fahrenheit, right? The T of 0 is equal to, let's see, 70, right? Plus C. All right, that must be equal to, the problem says that 35. Okay. So we got two unknowns with two, yeah, so from there, we can figure out K. From here, we can figure out C, right? So first one, let's say this is a 1, and this is the second equation. In our first equation, what? E to D, what's K? E to D negative 35K is what? 40 minus 70 over negative 35, right? So then K gonna be, is it? K is equal to what? Oh, oh really? Okay, thank you. So here is there is a C right here, right? Okay. So let's move this one to here. 35C, is it? Thank you. So K is equal to 1 over negative 35, right? Times natural log, yeah, natural log. And then 40 minus 70 over negative 35C. Is it? Okay, and then from second one, what's the C? C is equal to negative 25, oh, 35, right? Yeah. So we plug in C into right here. So we can figure out K. Okay. So the answer is 1 second. Let's see, K is, hold on a second. K is, from here, K is equal to negative 1/3 over natural log 6 over 7. This is approximately 0.05138. Okay. So that's the summary of the Newton's law of cooling. But please look at the example 1 on page 103. There is a time constant for the building. Time constant is this, 1 over t is equal to 1 over k. This is 1 over k is called the time constant. Okay. So because in general solution, when you solve this is special case, right? In this example, so when you solve dt over dt is equal to k times m minus t with initial time t of 0 is equal to t0, and then m of 0 is equal to m0. I mean, not initial condition. This is m of t is m0. Sorry. Okay, here. Okay. Then when you solve it, then it turns out that t of t is equal to m0 and plus t0 minus m0 times e to the negative k over t minus t0, actually. Okay. So using the method of inner factor or the separable, okay, just use either one, then you end up with that one. Okay. In case of that, the outside temperature is set to constant m sub 0. Okay, here. So look at this. If T0 is greater than M0, what happens? T0 is greater than M0, then the T of T is decreased. either way, what? This term just goes to 0, right? Because this is exponential function with a negative sign exponent, decreasing function. So approach 0. Okay, so T of T approaches M0 anyway. Anyway, so in here, when T is equal to 1 over K, okay? When T equals 1 over K with, let's say T0 equals 0. Oh, not T0, oops, sorry. Here, T0 equals 0, okay? Here. Then what? T of T becomes M0, all right? And then plus T0 minus M0 over E, okay? So now, what? A certain time T, then make this one to the constant is called the time constant, actually. This is a constant, right? So that, what time we got the constant? 1 over K. Okay. Okay. And then also the, okay, so still, the something, is there something else that makes this one special? Yes, when T equals to 1 over K, we got this one, you see that over E. So T, it means that the temperature is changed exponentially. So what temperature change exponentially, that happened when T equals 1 over K, which means that when T equals time constant, the temperature change exponentially. Okay, so that's the another meaning of time constant. So now okay, that's for the Newton's law of cooling.